Okay, so last time we have introduced this notion of ensembles. And the idea was that if we want to measure physical quantity, then one way would be to do the limit, to take time averages. This is what actually we should do on a particular trajectory of system. But this is a very complicated problem. And so the optimal thing to do is to instead introduce a density defined on the points which are visited by the system, and compute these averages on this density. So what this density must be is so the density, this density should be such that it is proportional to the frequency with which the system visits that point in phase space. And the interpretation which we want to give to this density is that we are considering not a system, a single system, but a number of ideal copies of the same system. Each of them which is consistent with the same macroscopic state. Okay? So all these systems are, so we think of this density as being the density of points in the phase space which represent microscopic states which are all consistent with the same macroscopic state. Okay? And of course, since the trajectory of the system in the phase space follows the laws of mechanics, then this tells us something about what this density must be. And this is given by the Liouville theorem, which we have described last time. So the Liouville theorem states that the density is this density here is a constant of the motion. So if you sit on a particular system and you follow its trajectory in the phase space, then and you think of measuring this number, you will see that this number is constant. Okay? So this is very, very important because it is very, very important because, of course, already from here to here we have simplified the problem of not having to solve the dynamical equations, but just having to compute this density. Still, this density is a function of 6n coordinates, so it's a very complicated object. Now, this thing tells us that rho is actually a constant of the motion. Okay? So the first thing is that this must be a function of the constant of the motions, and in particular of the Hamiltonian. And it is very important because now instead of having to compute a function of 6n coordinates, we just have to find what is this function f here. Okay. Okay, here, however, as we said yesterday, on Friday, there is an assumption, which is this ergodic assumption, That is, the Liouville theorem tells us that all the states which are visited will have the same value of rho, and will have also the same values of the energy if it is an isolated system. The converse is not true. I mean, it is not true that all the values with the same energy will be visited. Okay? So, but we will visit, we will work within these ergodic assumptions. Okay? And we have seen that this is a non-trivial type of assumption. In particular, in some cases, it involves a notion that the system be chaotic enough or disordered enough so that particles are really not orderly moving, but doing some chaotic motion, bouncing one with the other, so that they visit the whole accessible phase space with that constant energy. Okay, but we will not go further in this discussion, which is a very it's a very interesting discussion, which has to do with the kinetic theory. With the kinetic theory, we will not discuss very much the kinetic theory. But the other thing which we mentioned is that essentially this condition here means essentially that if you look at the trajectories in phase space of the system, then these trajectories never merge. Okay, so they are. I mean, if you are two systems, then their trajectories will not merge. Okay, they will always remain distinct. Okay, so if you want, if you are taking a volume, if you are taking a number of systems that evolves in time, and you look at the number of points as they evolve in time, you can always the number of distinct trajectory or the number of distinct points will always be conserved. Okay. Okay, so now what we need to do is to discuss what possible functions we can have here. And essentially, if we have an isolated system, that we know that for an isolated system, all the energy is conserved. And, or if you want, the energy, we can also say that the energy is conserved within a small range delta of the energy. So all the states which are visited are those where the energy will be in this small range. Okay. And then the density, of course, will be 0 if for all the points QP such that the Hamiltonian has an energy which is outside this range. And if the energy is inside this range, then it will be just constant. Okay? So let me write it like this. If is in the range Okay? Where this gamma of E will be the normalization condition. So gamma of E will be the integral of dq dp will be the volume of points which satisfy this condition, where h of q and p is less than p plus delta and larger than p. Okay? Okay, so this is called microcanonical ensemble. So this density here, or the corresponding ensemble of systems which it describes, is called microcanonical. Okay, and it describes isolated systems. Systems with essentially a conserved energy. Now the point is, how do we make contact between this density here and the things we want to measure, the macroscopic quantities? Okay, we have said that if all we need to do in order to compute thermodynamic quantities is to compute this number, which is the number of microstate which correspond to a macrostate. Okay, so one idea would be to have here we could think of a point of the 6n-dimensional phase space to correspond to a microstate. And then we could just say that this is just the log of the volume of phase space. Okay. Now, however, there is a problem with this. What is the problem? What are the dimensions of this? Huh? Yeah. Yeah. So this is an I-dimensional quantity. Okay. Whereas, what are the dimensions of this? This is a number. Okay. So we want to have a number here. Okay. So what we need to have here is divide this by an elementary volume, gamma 0. And we need to find this volume gamma 0, which would correspond to the volume, which will tell us what is the volume in phase space which corresponds to 1 microstate. Okay? And actually, it is not possible to determine this number within classical mechanics. Within classical mechanics, you see, unless you are able to determine this number, it should be the log. Okay. Log. There should be no log here. Sorry. So the number of microstate is the volume divided by the volume of a single macrostate. Okay, and then we are going to define the entropy as the log of this, as k times the log of this. So k times the log of gamma of E divided by gamma 0. Okay? So unless we are able to identify gamma 0, we cannot determine what is the zero of the, so the entropy will be determined up to an additive constant. Okay, and in classical mechanics, we cannot determine this this additive constant. Okay. So one way to do this is to take again the ideal gas. For the ideal gas, we have already computed this. You remember we have already computed the entropy of the ideal gas. So we can compute this gamma of E for the ideal gas in classical mechanics and compare it with the known result and infer what this gamma 0 should be. Okay. So what is this gamma of E for the ideal classical gas? Well, the ideal classical gas, the Hamiltonian is 1/2 P squared over M. So we are interested in computing this object, and the coordinates are all constrained to be in the volume, in a volume. Such that 1/2 1 over P squared over 2M is less E plus D delta less D. Okay? So this is the thing we have to compute. Okay? Now this integral is very easy. It's just the volume to the power n. Okay? And this object is also easy because, well, I can, it's just the volume the difference between the volume of two spheres right? So this is the volume of, so this is the integral of this energy for all the states with energy less than E plus delta. And I subtract to this all the states with energy less than E. Okay? Now if I look at these integrals here, these are just the volume of a sphere in 3n dimensions. Okay? And we have already done this calculation. You remember? So and we have volume to the n. And the volume of a sphere in 3n dimension is the radius of the sphere. The radius is square root 2m times E plus delta. To the power 3n times the volume of the unit the unit volume in 3n dimension, which is pi to the 3n over 2 divided by 3n over 2 factorial. Okay, and then I have this minus the same thing. pi 3 n 2. Okay. Very good. So now I want to take the log of these. And when I take the log of this, I have n times log v. Then I have this factor here. What I can take out is this factor here of pi 3 n over 2 over 3 n factorial times 2n 3 n over 2. And then I will have the log of this, of the square root of, well, of 2 of e plus delta. I mean, if you do the calculation, so this is because I'm taking this factor and this factor out, so what I am left is this divided by this with 3n over 2 minus 1. Okay, so this part, this part and this part are all proportional to n. This part is not proportional to n, so it's very small, and indeed when delta is small, this part will be, when delta is small with respect to the energy E, I can essentially neglect this part. And of course I have minus the log of this gamma 0. So now if you take this equation here and you compare it to the equation which we have derived for the ideal gas, you can get what gamma 0 should be. And from this you get that gamma 0 must be equal to h to the 3n. Okay? Okay, so why do we get this? So you see, we get that this tells us that the volume in phase space which corresponds to 1 microstate is proportional to Planck's constant to the number to 3n, the number of degrees of freedom times 2. Okay, and so there is a reason for this. Well, there is a reason for this, which is essentially Heisenberg uncertainty principle. Which tell us that if you have a particle, say a one-dimensional particle, then you cannot measure its position and its moment to an accuracy such that the product of the error which you get on the position and the momentum is less than h bar. Okay. So this tells us that there is a volume or there is a volume of phase space which we cannot actually inside which we cannot really distinguish points. Okay, and so this is the natural definition of a microstate, because we cannot distinguish anything below this volume. Okay, and actually, if you think about well, a single say if you think about a single particle, and you look at what is the so what is the so this tells you that in the phase space of a single particle, if the energy is conserved, so all the points which are such that the indeterminacy on the Q or indeterminacy times the indeterminacy on P is less than h bar. So all these points cannot be distinguished. And this essentially is equal to, is equivalent to the surface of a sphere with radius h bar. And so this tells us that it is natural to think that for n equal to 1, so the volume which I should use there is essentially 2 pi times this indeterminacy, which is 2 pi times h bar, which is h. Okay. Now, I want to convince you that a little bit more clearly about this relation. So let us consider another system. Okay. Yeah, please.
So that relationship there, when you say n is equals to 1,
yeah,
implies that there is one particle and the volume is h.
Yes. So what I'm saying is that for one particle, you cannot really distinguish the points on this surface. Okay. And so the volume which corresponds to one microstate should be equal to this. But I want to make this correspondence even clearer for the harmonic oscillator, where we can do it really more precisely. So let me consider the so for the harmonic oscillator, what I want to consider is just the case of one particle in one dimension. Okay, so very, very simple. Very, very simple. And then I want to compute the volume in phase space corresponding to energy E. Okay? Now, okay, so the Hamiltonian is what? The Hamiltonian is kinetic energy plus elastic energy, right? Okay, so this is the frequency and this is the mass. Okay? And so I want to, so let me compute the volume in phase space of all points which have energy less or equal to E. Okay? So since I used, let me call this gamma of E. Okay? So gamma of E is the integral when the Hamiltonian is less than E dq dt. Okay. Now this is again a simple calculation, because if you think about what this particle, what are the what is this volume here in phase space? Phase space just two-dimensional space here. So these are just ellipses. Okay? So this is the volume I want to compute. Okay? And the way, so one way to compute this volume is to change variables and call, for example, x, call xp divided by square root 2m times E, and y is q divided by square root 2 E divided by m omega squared. Okay. If I do this, this constraint here becomes that x squared plus y squared must be less or equal to 1. Okay. So then I can compute this integral very easily, because I have just a change of variable. So I have a factor square root 2 m times E, which comes from the dp, a factor which is square root of 2E divided by m omega squared, which comes from the dq. And then I have the integral x squared plus y squared is equal to 1 dx dy. Okay? Now, this integral is simple, no? Is the area of this unit circle, which is pi. Okay? So this is just, I have a 2, m and m goes away, 2e over omega times pi. Very good. Now let me consider the quantum system. Okay, so so the result here is that the volume, which correspond to this energy, is 2 pi e over omega. Okay. Now let me consider the quantum system. The quantum system, you know it very well. So harmonic oscillator. The quantum harmonic oscillator, you know very well, there are discrete energy levels, and the energy of this discrete energy level is n plus 1/2 times h bar omega. Okay? So the same system there, classical system, would be correspond would correspond to a system with discrete energy levels of this. So which tells you that inside a volume of energy E, so inside a volume, so inside this volume of energy En, there are n states. Okay. So you can compute how many. So if you want to understand what is the volume, so you want to say that the elementary volume of one microstate, in this case, is just the difference between the volume which corresponds to n plus 1 states and the volume which corresponds to n states. Okay? So this one is 2 pi over omega times En, which is n plus 3 half h bar omega. And this one is 2 pi over omega n plus 1 half h bar omega. Okay? Yeah?
Why we don't, I know that we don't consider this as a state, but why we don't consider vacuum as a state? Because in the
Why we don't consider
vacuum,
vacuum?
yes, as a state, because in the form
Vacuum is this 1/2, right?
this is the nature of the vacuum. So
Okay, so the vacuum, so there will be a volume of phase space which corresponds to the vacuum. But here we are interested in computing how much volume is occupied by one state. So, and I'm taking I'm saying if I take the volume of n states and increase by one state, how much more volume should I? How much does the volume in phase space increases? And this will be the volume of one microstate. Okay, so you see the vacuum. When I take this difference, the vacuum cancels. Okay.
but in the formula of En,
Yeah.
we have the energy of vacuum.
Yes.
But you say we have n states. Okay.
Yes. So let's say this would be the volume which corresponds to En, and this will be the volume which corresponds to En plus 1. There is also the volume which corresponds to E0. Okay? So there is a volume which corresponds to E0. But what I want to say is that the volume which corresponds to one microstate is this one. When I go from n to n plus 1, how much more volume in phase space is there for one particle, for 1 degree of freedom? Okay? And of course, I mean, this is this volume here of this ring does not depend on the fact that there is a vacuum here, because essentially in this calculation you see it cancels. Okay, and if you do this calculation, you get 2 pi h bar, so you get that this gamma is just h. Okay, does this convince you?
Yes, gamma zero is correct, but why in the formula of En we don't consider the vacuum as a state, since we have the energy of vacuum in En. So you said we have n states, but in the En we have the energy of the vacuum.
Yeah.
It looks like we have n state plus 1, which gives us the vacuum energy.
Okay. So you are saying I start considering the states from the first one. Okay. So yes. Okay. Okay. You could call this en plus 1 if you want, and then there will be 1/2 here and minus 1/2 here, but the result will be the same. Okay. Yes. So okay. It's customary to call E0 the vacuum. Okay, so and now so we have seen so that for 1 degree of freedom the correct volume corresponding to one state is H. Now if I have n degrees of freedom and if they are independent, of course I can do this, the volume will be the volume of 1 degree of freedom to the power n, and so for n degrees of freedom the gamma 0 will be just h to the n. Okay, and so the recipe in the microcanonical ensemble is that the number of states of microstate, a certain number of particle volume and energy, is equal to the volume of phase space divided by h to the 3n. Okay. So all you have to do is to compute these numbers here for a particular system divided by h to the 3n, and then this gives you the number of states, and then you can compute thermodynamics. Okay, this is the recipe for isolated systems. Okay, are there questions? Yeah.
Isolated system has discretization of the phase space with H.
Mm-hmm.
It's intrinsic property of isolated system.
See, it's an intrinsic property of bounded systems in quantum mechanics. If you have a quantum mechanical system in a finite region of space, this will have quantized energy levels, right? And then each of these energy levels will occupy in phase space a volume which is essentially h to the 3n. Now the fact that there are discrete energy levels comes from the fact that it is a confined system, right? No. So for an ideal gas, you have plane waves. But for a harmonic oscillator, you don't even need a confinement because there is a potential which is confining the particle, right? And then yes. Yeah.
It's just a kind of the natural size of the microstate.
The natural, yes, the volume in phase space which corresponds to one microstate is h to the 3n. Yeah.
Okay. Is it possible to measure experimentally this way?
It is experimentally. Well, there are consequences. There are consequences of this volume, which are well, which have to do with so this number, if you remember, enters into the final expression of the entropy. Okay, so if you have of the ideal gas, for example, so if you are able to compute the entropy, then you can get a measure of this number, and indeed this number was first suggested. I mean, the formula for the ideal gas, the formula which we wrote down for the ideal gas, was actually developed before quantum mechanics was fully developed. And the value of the constant of h was predicted on the basis that you wanted the zero of the entropy to be at temperature 0. Okay. So if you require this property, you get you can measure h bar if you want. Okay. You just extrapolate say the entropy of an ideal gas which measures a high temperature to 0, and with the formula which is given by which we wrote down, and you require that the entropy at temperature 0 be equal to 0, and this gives you a measure of this quantity here. So it's rather remarkable that you have quantum effects which enter into a formula which describe a completely classical system, such as an ideal gas, but essentially quantum effects are no play no role. Is this clear? Is this?
So, if we want to go through the quantum scale, we have to divide all volume by this number.
Yes, yes, for two reasons. One is that you want to make this number i-dimensional, and of course h has the correct dimensions. No, right? So the fact that since this is an integral on dq and dp over n particles, so you need something which has the scale of h to the 3n, the dimension of h to the 3n. And then the numerical value is given by the correspondence with quantum mechanics. Okay.
So we can do the same with, for example, this room. Volume of this room divide by this number.
No, I'm talking about this is the volume in phase space. Okay. It's not the volume, the physical volume.
What means phase space?
Huh?
What means phase space?
Well, it's a sort of abstraction. So you should think that each position of each of the particles of the gas in this room and each momentum of the particles in this room, it's a point in this phase space. So phase space is a very high dimensional space, where each point has a number of coordinates which is 6 times the number of particles. Okay? So each of these each of these coordinates is the momentum or the coordinate along one of the direction of one of the particles. Okay. And of course, I mean, each different configuration of the gas in this room is a different point. And all these points occupy a certain region in this space, this 6 n-dimensional space. And this thing is the volume of this region, of the region of all these points which have the same energy. Okay? It's a bit of an abstract concept. So, but it's very useful because then you can relate it to this number here, which is the number of microstates, and which you can relate it to thermodynamic quantities, as we have discussed last time, right? And so the other thing is, we have already said that this is a really not even astronomical. This is a huge number. I mean, it's a really large number. This is proportional to exponential of the number of particles. The number of particles is 10 to the 23. It's Avogadro's number. Okay. So this is also a huge, I mean, a very, very large number. Okay. A very, very large volume. Okay. So.
Okay, if I consider, if I take the volume to be large, then I can consider that the gas particles are free, and then I can think of a plane wave for each particle. And then why is that the minimum volume for the microphysics H? Is it the same?
Sorry?
Let's take the volume to be large.
Yes, yeah.
So
you have to impose. Huh?
Okay, now I think if I take the volume to be large, then they behave as if free. I mean, there is as if there is no boundary.
Well, no, because you have to put boundary conditions on the plane wave, right?
So
and this gives you the energy levels. And that is where the volume enters into the calculation. No? You remember, so the K must be 2 pi n divided by the length of the box. And the length of the box is volume to the 1/3. So that is where the volume enters. So the space, you see, the spacing between the energy levels goes down as the volume gets larger. No? So the difference in a, so since the K is 2 pi by volume to the 1/3 times an integer, and the energy is essentially proportional to K squared, this is proportional to volume to the -2/3. Okay? So the difference between two nearby levels goes down as the volume to the 2/3. So when the volume gets large, you get a continuum, essentially a continuum spectrum of energy.
Do we have a volume for the microstate H?
Yes. Then essentially what we have done in the first lecture is to compute this number here from really quantum mechanics, counting the states, really counting the quantum states. And what we have done today is to compute this number by integrating on the phase space volume. And if you compare the two calculations, you get this number here. Okay, so it's precisely what we did. Okay. Okay, so this was the microcanonical ensemble. Well, there are reasons why is not practical to use the microcanonical ensemble as a description because in many cases you don't deal with an isolated system. In many cases, say for example, if you deal with the gas in this room, it is not an isolated system because it is in contact with the walls and with the gas outside. So it will be in thermal equilibrium, if you want, with the gas outside, or well, not in thermal equilibrium because it's air conditioning. But so so rather than considering, rather than having a description of isolated system, we would like to have a description of systems which are in thermal equilibrium with other systems, other maybe larger systems. Okay. The reason is also that experimentally, it is not easy to measure or control the energy of a system. It is simpler to measure or control the temperature of a system. Okay. You measure the temperature of a system just by a thermometer. Okay. Measuring the energy is instead more complicated. Okay. So this is why we would like to discuss systems in thermal equilibrium. And the key question is what is the density in the phase space which correspond to this system, or what is the function? We know that this must be a function of the energy. What will be this function? What will this function be? Okay. And so I want to give you, say, two arguments for this function. So the first one is, so we want to consider a system A which is in thermal equilibrium with another system. So this will have a certain number of particles, a certain volume, and the energy will not be fixed. What will be fixed is the temperature, which will be equal to the temperature of the larger system. Okay. Typically, this is what you do if you want to take a system and bring it to a particular temperature. You put it into a heat bath. A heat bath is a larger system whose temperature is controlled, and it's equal to the temperature at which you want to bring this system. Okay. So this larger system is called heat bath. And the way this system will get at a particular temperature T, which is controlled in this heat bath, is that it will exchange heat with it. And at a certain point, when the exchange of it goes to zero, they will be in equilibrium at the same temperature. Now, typically, this heat bath will be much larger system than the system we are interested in. Okay, because why should it be much larger? Because we don't want. Well, we want that the property of this system to influence the properties of this other system. We don't want that the heat bath changes its property as a result of transformation which occur in our system. Okay. Okay, so one idea to figure out what this density should be is to imagine the following situation, where instead of having just one system, you have two systems. So imagine that you have one system here and another system here. Call it A2. Now these two systems are both in thermal equilibrium with the same heat bath. Okay? But the heat bath is very large and they are far apart one with respect to the other. Okay? So that apart from knowing that they are both in thermal equilibrium with this system, knowing the state, or in particular the microstate of this system, does not tell you anything about the microstate of this other system. What mathematically what I'm referring to is the fact that if you consider the joint distribution of the two systems, which depends on the coordinate and the moment of system 1 and system 2, then these must be factorized. Okay? The two systems should be independent. Okay? So this is a statement that tells you that if you know something about system 1, then this tells you nothing about what is the microstate of system 2. Okay? Now the other thing that we know is that the total energy of the total system, so the Hamiltonian of the combined system, is just the sum of the Hamiltonians. Which, if we assume that the systems are the same, of the same nature, I mean, for example, the same gas or the same piece of material, so the functional form will be the same. Okay. Now, in order to find this function here, notice that now if you take if you take the log of rho 1, 2, this will be the sum of the log of rho 1 plus the log of rho 2. Okay? And so if so this rho 1, 2 must be a function of h12. This must be a function of h of coordinates q1, p1, and this must be a function of h of q2 and p2. So must be the log of these quantities. Okay. So, but the log of the combined system is the sum of the two of the log of the density of the two systems, and the Hamiltonian is also the sum. Okay. So the only function f which you can think of is such that the log of rho must be linear in h, or that rho must be exponential in h. Okay? So if you combine these three properties, it tells you that rho of q and p must be equal to e to the divided by a normalization constant. Okay? So this is the only functional form which is consistent with the fact that the energy is extensive and that the two systems must be independent. Okay? And so this is called the canonical ensemble. So this is called canonical ensemble. Now, still we don't know what is, yep.
Could you please repeat how you come up with
Because if you take the log here, the log of the combined system will be minus beta times the Hamiltonian of the two of the combined system, which is this. If you take the log of rho 1 using that, it will be proportion minus beta 2 times the Hamiltonian of system 1. And if you take the log of rho 2, it will be minus beta of the times the Hamiltonian of 2. So these two equations will be satisfied if you take that functional form. Okay? If you take any other functional form, it will not be satisfied. Okay? So because so if this is a function of the energy of the Hamiltonian, and the log of rho is an additive function on the subsystem, and if the energy is also additive on the subsystem, then the log must be linear in the energy. Okay? And we decide that the constant of proportionality, we call it minus beta. Okay? And now the question is to understand what is beta. Okay? But in general, this is the form which is consistent with the fact that these two subsystems are independent, and the only thing which is in common to them is that they are at the same temperature T. Okay? Okay? So, which, by the way, tells you that both these two systems will have a distribution which is of this type, but the beta must be the same. The beta of one system must be equal to the beta of the other system. Okay? Indeed, we are going to see that beta is related to the temperature. Okay? Very good. How do we do this? So the way we do this, let's go back to our system, which is in equilibrium, just one system in equilibrium with a heat bath. And of course, now the energy will be, the energy of the system will vary, because there will be exchange of heat between these two systems. Okay. Now the question we are interested in then is, in order to find this function here, is what is the probability that a particular state will have energy, a particular microstate of this system will have energy E. Okay? So let me call this probability is the, so this is the probability that a microstate has energy E. Okay. So let me put it differently. Sorry. So I know that a microstate has energy E. What is the probability that I will find a system in that microstate? Okay. To find the system A in microstate R with the energy of the microstate R equal to E. Okay. Sorry. So I have a particular microstate. I know that it has a certain energy, which is given by the Hamiltonian. Now I want to understand what is the probability to find the system in this microstate, which will tell me what is this function f, right? I mean, this is important because there may be many states with the same energy, okay? And so the probability to find the system with a certain energy will be equal to this probability times the number of states which have that energy. Okay. So indeed, yes, if you are interested in this probability here, then essentially what we know is what is the distribution of the larger system, because the larger system is a system which has constant energy. It is an isolated system. So it's described by the microcanonical ensemble. Described by a microcanonical ensemble, so all the states with a certain energy E0, which is equal to E of the state of the subsystem A, let me call it EA plus EA prime, which are constant. All these states will be equiprobable. Okay. And now, if I fix, if I fix one particular state with an energy which is equal to E of system A, then the probability to find this system in this particular system with energy E will be proportional to the number of ways in which I can have the rest of the system with energy or the rest of the system with energy E0 minus EA. Okay? And this is proportional to the number of microstate of the heat bath at energy E minus EA. Okay, so this probability here is proportional to omega prime of E0 minus E. So let me repeat. So the total system is described by a microcanonical ensemble. So every state is equally probable. Okay. Now I'm fixing this subsystem to be in a state with energy E. Okay. So I'm interested in what is the probability of that particular state where this subsystem has energy E. Okay. Now this probability will be proportional to the number of states in which the rest of the system, the heat bath, can be. Okay. So this is, and this will be given by the number of states of the heat bath at energy E0 minus E. Okay. Now we know that this is E to the K times the entropy of the heat bath. By this S prime, I refer to the entropy of the heat bath of the system A prime at energy E0 minus E. Now the other thing is that I'm considering that this system is very small compared to the rest of the system. So I am interested in energies where this energy is much more smaller than this. Or this energy is much more than the total system. Particularly, I'm interested, say, for example, in the limit where the heat bath, the size of the heat bath goes to infinity. And I'm considering a finite system. Okay? And then what I can do is to use Taylor expansion of this function here. Okay? So the entropy of the heat bath at energy E0 minus E is what? Is the energy of the heat bath at energy E0 plus the derivative of the entropy of the heat bath with respect to its energy computed in E bar equal to E0. And this is, of course, at N and B constant. Okay? Times minus E times the difference. Okay? And then there is the second order derivative, 1/2 d squared S dE squared computed in, this is always of the heat bath, E prime equal to E0 times E squared plus other terms. Okay? Now this is S prime of E0. This is 1 over KT. This is 1 over K times the temperature of the heat bath, which is the same temperature as the system. Okay? Times E plus this other term. Okay? So what I get from this is that the probability of E will be proportional to E to the minus E divided by KT plus other things. So now I want to convince you that these other things are very small. And in particular are essentially 0 when the size of the heat bath goes to infinity. The reason is that so d s squared, so the second derivative of the entropy with respect to the energy squared. Well, we know that this is the derivative with respect to the energy of 1 over kT, right? The derivative of the entropy with respect to the energy is 1 over kT. So this is minus 1 over kT squared times the derivative of the temperature with respect to E. And this is the inverse of the specific heat. The derivative of the energy at constant volume and number of particles with respect to the temperature is the specific heat. And this is the inverse of that. So this is minus 1 over kT squared times the CV. Now, the specific heat is extensive quantity. It's an extensive quantity. So it goes to, it increases when the size of the system goes to, increases. Okay? In particular, that is the specific heat of the heat bath. which is assumed to be very, very large because the heat bath is very, very large. In particular, when I send a heat bath to infinity, this part, this term will essentially go to 0. Okay. So the result is that if I'm interested in the probability of a particular state with a energy E, this will be proportional to e to the minus the energy divided by kT. And so you see this is the same result as before, where beta is equal to minus 1 over kT. Okay? And this is the canonical ensemble. Okay? So, in the canonical ensemble, the probability, so the rho of Q and P is equal to e to the minus, say, H, Q and P divided by KT. And the normalization constant which is a function of n, v, n, t. This normalization constant which will be in general just the integral dq over all coordinates and all momenta of e to the minus h qp divided by kt. This is called the partition function. Okay. Notice one thing that so essentially what you have to do in order to compute, well, we will see this next time. What you have to do to compute things in the canonical ensemble is to compute the partition function. Computing the partition function is easier than computing volumes in the phase space. Volume of phase space, because this integral is an integral on all the phase space. So there is no limit on this, there is no constraint on this. Well, if we are looking at the system in a finite volume V, then the integral on the coordinates will be limited in the volume. But the integral on the momenta have no, are from minus infinity to infinity in general. So typically this is easier calculation than is an easier calculation than in the case of the microcanonical ensemble. Okay. So questions. So is everything clear? So the recipe is if you have to describe a system in thermal equilibrium, then what you have to do is to take this density, a density of a microstate, which is constructed in this way. Well, of course, yes, and what we will see is that essentially you have to compute this partition function. And yeah.
Something not clear from the, when we describe the microcanonical system, we say that each microstate is equally probable.
Yes.
And now we are finding the in the.
Yes, yes. So now we are saying, so the question is, in the microcanonical ensemble, we have this assumption that all the states are equally probable. And now we are saying that the states are not all equally probable. And the reason is that, I mean, the state of this system are not all equally probable. There are some which are more probable and some which are less probable. And the reason is that we are not imposing a constraint on this system to have a finite energy, a given energy. So the energy can fluctuate. So there may be some some fluctuation by which this system gives some heat to the subsystem. And there may be very rare event in which there are several of these fluctuations, so that the energy of in this subsystem goes up. And so the system, this subsystem will visit many states with different energies. And of course, state with the same energy should have the same probability. Okay, this is this. States with different energy will have different probabilities, right? And so how you give probabilities to states with different energies, this is the answer, okay? So the correct way to give probabilities to states with different energy is the canonical ensemble.
We are also changing the number of microstates in our system if there is change in energy.
So the number of microstates of your system, yes, it's changing. It's changing, no, because it's changing with the energy, no, and yeah, sure, yeah, it will be related to the entropy, no. You see, before I was discussing things in the microcanonical ensemble. I was discussing things when the number of particles, the volume, and the energy were fixed. And so the entropy was fixed because it was a function of these three things. Now I'm discussing things where the number of particles, the volume, and the temperature are fixed. So the energy is not fixed. It can fluctuate. And the entropy also will fluctuate, will not be fixed. Okay? So and this is precisely what you say. The number of microstates will not be fixed, will fluctuate. Okay? Yeah. Okay, so see you on Friday, on Wednesday. Yes.